Okay, so do you see my screen?
Yes, sir.
Okay. Okay, so let us try to solve some exercises. Consider these two languages, A and B. A consists of strings of the form. Okay. Okay. So I think I should mention some more thing. Okay. Okay. Maybe before this. Sorry. Yeah. So the difference between these two languages, A and B, is that both consist of strings of the form xy. X and y are coming from AB star. The condition is the same. Number of A's in X is equal to number of B's in Y. Here it is given that they are separated by $1, this X and Y. And here there is no, boundary between this X and Y. Okay. So it is given that one of these two sets is regular, the other one is not. Which one is what and why?
Sir, the first one is not regular.
First one is not regular. Why?
Sir, we can take the string a power k dollar b power k. So u equal to epsilon, v equal to a power k, and w equal to dollar b power k, where k is a pumping lemma constant.
Okay. So that's good. So A is not regular. So how to prove this? Suppose A is regular. K, a pumping lemma constant for A. Then take U equal to epsilon, V equal to a power K, W equal to dollar b power K. Okay. And then proceed. Okay, so pumping in or out will happen in V. If you pump in or out, you are simply changing the number of A's. The number of B's continues to stay the same, K. Okay. So by this statement, it follows that B is regular. But if I want to proceed this way, if I take U equal to epsilon, V equal to a power K, W equal to B power K, what is the problem with this proof?
So if we pump some extra A's, then we can say that those many A's and B power K are the new Y, and still are the new Y. Means some of the A's from X we can say that they are in Y.
Okay. So for example, if you pump out, string will be of the form a power K minus L, b power K, where L is the length of the pumped thing, but I can anyway write it as K minus L. If you pump in, I can write this as A power K, A power L, B power K. This way we cannot arrive at any contradiction. Anyway, so this proof fails. We have still not proved that B is regular.
Sir, X and Y can be empty as well, right?
Yes, yes.
Sir, doesn't that make B equal to sigma star itself?
Is sigma star. Now, if you say B equal to sigma star, okay, sigma is A comma B here. There should be a justification. Why is it so? Yes, this is correct. Every string can be decomposed in the form xy such that the number of A in X is equal to the number of B in Y. Why?
Sir, if we take a, for example, for the ith index, if we take the number of A's for the first I characters minus the number of B's in the characters that appear after the ith character, this variable, let's say for I equal to 0, that is when the when X is empty and Y is the full string, this value be X. This value be let's say M. Then when I equal to the length of the string and this value becomes minus M, so it must hit 0 at some point of time.
I minus M?
Because the number of A's must be the opposite.
I didn't say equal number of A's and equal number of B's in the total string. Look at this string, A power.
Even if it is not equal, let's say it goes from plus K to minus N minus L. So from plus K to minus L, it has to hit 0 in somewhere in between, right?
Why does it hit 0 for this string?
Sir, we can take X as epsilon.
This is true for this example, but why is this true for? You can see that the number of A's, number of B's, it goes like this 0, 1, 2 up to K. Never reaches 0 except at the beginning. So that proof is not valid, right?
Okay, sir. Yes, sir.
But I can still take X equal to epsilon and Y equal to A power K. Okay, so one thing is obvious, B is definitely contained in A B star. So I have to prove only this part. So take any Z in A B star to show that Z is in B. Okay. This is nothing but just a restatement of what we are supposed to prove. How should I proceed? No idea? How should I proceed?
Sir, induction
Do
on
that,
the side.
right?
Yes. So induction on the length of Z. This is one way of doing it. There may be other way also, but anyway. So, so if this is 0, then Z is epsilon, and this can be written as epsilon epsilon. Number of A's in this epsilon is 0, number of B's in this epsilon is again 0. So now suppose I am considering non-empty strings. Okay. So, and there is another character here. So this is my Z. Okay. Now by induction hypothesis, this has a decomposition. This is my X, this is my Y. So number of A's here is equal to number of B's here, this part. Now there are two possibilities for this. This is A, this is B. Okay. If this is A, what should I do?
So it is already satisfied.
Okay, so I'll simply include this A in this Y. Okay, so number of X's, number of A's in this part is equal to number of B's. If I add an A, nothing happens. The number of B's does not change in this part. If it is B, so this is easy.
So we will shift the partition by one character.
How? I didn't say this is non-empty. This may be empty also.
Instead of inserting A or B at the end, if we inserted it in the middle, wouldn't it be simpler to prove?
I do not think
Between
so.
X or Y.
I do not think so. Maybe you can think about doing it. Anyway, so there are several cases actually. X, let us call this Y. So one possibility is that Y is empty. What does it imply about X?
X has no A's.
X only consists of B's, right?
Yes, sir.
It will be of the form B power K for some K greater than equal to 0. And if K is 0,
Epsilon.
so the string will be epsilon epsilon B. And I can write it as B epsilon. Number of A's in B is 0, number of A's in that B is 0, number of B's in epsilon is also 0. Okay. If K is greater than 0,
So we'll append that B to X itself.
I will simply append that B to itself. Okay. So in all the cases, I could solve it. Otherwise, if Y is not epsilon, then something will appear here. If that is A, I will simply shift this boundary from here to here, right? If this is A.
Yes, sir.
Okay, so the number of A's become one more in X part, and this is compensated for by this new B. If it is B, Then also it is fine. I
So
will
then
shift,
also we'll shift by 1.
will shift the boundary. The number of A's does not increase in this X part, extended X part, but number of B's in this part, new Y, reduces by 1. Reduces by 1 here and plus 1 here. So it remains the same. Okay. Okay, so in all the cases, I could manage to decompose this new string of length, the earlier string plus 1, such that I continue to have a decomposition of this form. Okay. Okay, so I'm not writing this. It's fairly straightforward to visualize. Okay. So,
Sir?
Yeah, tell me.
Sir, in the previous proof, sir, why does not it work? I mean, if there are p number of A's and q number of B's, the variable a minus a in the left part minus b in the right part, when the partition is at the leftmost point is minus q, and when the partition is in the right, it is p. So if p and q are none of them are, if one of them is 0, then we are done, and if none of them are 0, then for each movement the variable can only change by 1 and hence must hit 0 at one point of time.
No, that's what I gave you this example, a power k. It never becomes 0, right?
Yes, sir.
Yeah, it
So
becomes 0
it becomes 0 at the
at
first,
the end only.
At the end.
so p equal to
Sorry,
p
at
equal
the
to 0.
start only. At the start only.
It is always 0, right? Irrespective of the string, it is always 0 at the beginning.
No, sir.
Yes, sir. And so we are done, right? So
No,
we
sir. For
partition
a
at
to
the
the
beginning.
k b, it would be 1, sir.
What?
Sir, for a to the power
A to
k
the
b, it would be 1.
A to the power kb, it will be 1.
Yes, sir, because we are taking the number of, sir, it would be minus 1
It will
because we are
minus
taking
1.
taking the number of A's in the left side minus the number of B's in the right side.
Oh, number of B's in the left side. Okay, your definition was something different. Anyway, you think about this. There may be other ways of doing this. Okay. Anyway, so I thought it's the number of A's up to this point minus number of B's up to this point. So this is how I define this here. Anyway, there may be other ways. Anyway, so this is no longer a really, I would say, formal language proof. It's just a discrete structure proof. But if you want to go ahead with the discrete structure proof that I will not do it because this is not pertinent to this course. Prove that this decomposition is unique. You cannot have two different decomposition of this form. Okay. So it's an interesting idea. You think about this. Okay.
Can you explain what do you mean by that? Decomposition is
Every z can be decomposed into xy such that the number of a's in x is equal to number of b's in y. And that decomposition is unique. You cannot write it as xy and x prime y prime, both satisfying the same property. Okay. But anyway, this is the discrete structure exercise. Let us move on. Okay. Okay, so let L be a regular language. Okay. So I am defining the duplicate of L as the set of all strings of the form WW such that W is in L. So earlier in possibly last tutorial, you have looked at something called half of L. Set of all W such that WW is in L. Do you remember?
Yes, sir.
Okay, so I'm just now reversing the construction. Take every string in L, duplicate it. That way I generate this language tuple. Okay. Now, one of these three conditions must be necessarily true. If L is regular, this must be regular, this must be non-regular, or it may or may not be regular. So which one is true?
Sir, may or may not be regular.
Why?
Sir, for finite sets of L, it is definitely regular because duplicate of L is regular. And for any set, it might not be regular.
No, but you have to give an example. Otherwise,
Okay, sir. Yes, sir. Yes, sir. We take L equal to sigma, and then W equal to A power K, B power K. So WW becomes A power K, B power K, A power K, B power K. That cannot. And we apply.
A power K, B power K is not regular.
No, sir. It is a part of sigma.
I didn't understand.
Sir, we take L equal to sigma star.
L equal to sigma star, okay?
And assume that duplicate of L is regular.
Okay.
And then we take the string for a given pumping lemma constant K.
Okay, so A power K, B power K comes in your pumping lemma proof. Okay.
Yes,
fine.
sir.
Okay. Okay, so C is true. May be regular. Take L finite. Another possibility is you can take L language of A star. What will be dupe of L? L is language of A star.
Even
what
number
is
of even length of A's.
That is clearly regular, right? In this
Yes.
case, dupe of L is language of A star. And here you can take L equal to language of A plus B star. Okay. The pumping lemma proof. Take this string A power K, B power K, A power K, B power K, and some block you take as U. Maybe this one is U. This as V, this as W. Okay. Okay, so this proof is fairly straightforward. So I am leaving it to you. Okay. So now there are, actually we have seen a language, W contains an equal number of occurrences of A and B. Now I am asking, yeah.
In the previous using pumping lemma also, if we take some constant L and B power K minus L will also be in this L, right? Because there is no constraint on number of.
What did you say?
Here we are taking V as B power K.
Yeah.
So B power K minus L, K plus L, everything will be in L, right?
Why? It is not the duplicate of anything. If I just take out some L number of B's here, A power K, B power K minus L, then A power K, B power K. How is it a duplicate of a string?
It's not duplicate of a string, but it is in L, right?
Sorry.
Yes, sir. It is not in duplicate of L.
It's not in duplicate of L, yeah. I have taken L, yeah. It's not in duplicate of L, yes. Okay. Okay, so recall that W contains an equal number of occurrences of A and B. That is not regular. We have already proved it. Now I'm asking the same questions with A and B replaced by AB and BA. and in the second case, AAB and BBA. So which of these are regular or is regular? Which is or are not?
First one is regular
One is regular.
because we can just simply create a DFA for it.
Mm.
It just says that the first letter and the last letter have to be same. Because once we get an AB, the last letter changes and then BA gives us the same thing.
That's all right. Any string with first letter and last letter same qualifies for being in A, right? Yeah, it seems so. Okay, so A is regular. For example, I can draw this, design this DFA. A, B. This is also an accept state. Okay, as long as I keep on reading A, it's fine. But if I read a B, then I have to read another A, right? Before accepting. So I can have this. Here also, as long as there is B, I will stay here. If I read A, I come here and keep on reading A, and then B. Okay, fine. So first and last letters are the same. What about B?
So can I take U as AAP and V as BBA?
You take? Yeah, please.
U as AAP. U.
AB. No, so your verdict is that this is not regular. B is not regular.
Yes, sir.
Okay. Okay. So the first suggestion is that B is not regular. Then I have to use some kind of proof, like in pumping lemma. So what is your suggestion?
U equals to AAP.
AAB.
B is BBA.
B is
BBA.
BBA.
Yes, sir. And the remaining thing is epsilon.
B is BBA.
Yes, sir.
So there is nothing about the pumping lemma constant, nothing.
So like number of BBAs might change also after pumping lemma.
Where is K, the pumping lemma constant?
Yes, sir.
I have to ensure that the total, I mean, the length of this B is greater than equal to K. Otherwise, this game will not proceed, right?
Okay, sir. Okay.
So let's say we take BBA over to the K.
Over to the power K. Okay. Then what will be U and what will be W?
U and W, I'll just take A, B, and epsilon.
This is all to the power K. The number of BBA will be something like K, and whereas number of AAB.
Oh no. Okay, so AB to the K. Okay. AB to the K. Here is AB to the K and to the K.
Okay.
Now there will be a decomposition
of B. Okay, so it's of the form AAB, 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 and then I have BBA, BBA, BBA. Okay. So now this can be decomposed of the form XYZ. Suppose the decomposition gives X equal to epsilon, Y equal to B. Is there a contradiction?
So can we do a pumping lemma proof for like different case differently? Like let's say K greater than 3 in a different way, K less than 3 in a different way. Can I do it like that?
Yeah, you can do that. But if X is epsilon, Y is B, there is no contradiction, right? Because
Yes.
this B clubbed together with this BA will keep the number of BBAs the same.
Okay, so we, if we just delete that B from the end of U, we won't take that thing. AB to the K minus 1 and then AA. That
Okay,
will be
so
our U.
something like that you have to do. And another possibility is you just take U equal to on a +1. Okay. So if this ends with A, even if this B is removed, we cannot have a situation like this. Okay, or you can remove this from whatever. And you can see, so I have just added one more A. Okay, so I have included this part in my X. U, not X. This is V. Makes sense, right? Yes. Okay. So now if I remove this Y, the number of B's and A's will be too, either one of this will be too small compared to the number of, okay. Okay, so you formally write this proof. Maybe how much time? Okay, maybe this one, what about this? Okay, maybe let us do this. Okay, so let's consider a set of positive integers. A, and consider binary A, the set of all binary representation of elements of A, and unary A, set of all unary representation, that is 0 power n in A. Okay, so now there are two statements. If unary A is regular, then binary A is regular. If binary A is regular, then unary A is regular. For example, if A is the set of all primes, okay, 2, 3, 5, 7, then what is binary A? It's like 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, and so on. And of course, you may add some leading zeros. You may also include 0, 1, 0, 0, 0, 1, 0. This is also fine. If you allow leading 0 digits or bits, whereas unary A is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 7 zeros, and so on. Okay. So I hope this definition is clear to you. So now we'll go ahead and prove or disprove each of these two statements.
Sir, for the B part, we can use that last class proof that if B is regular, then length of A should be in UP. Then length of
So what is the conclusion? First, let me know. A is true, B is true, A is false, B is false. Then we will start trying to prove it.
Okay, sir.
Sir, B is false.
B is false. If it is false, then you have to give an example.
Sir, we take binary of A equals 1, 1, 1, 1, 1, 1, and so on, like 1 star basically. And we observe that lengths of unary of A is same as A, and A is not ultimately periodic. So unary of A cannot be regular.
Okay, so for B, your suggestion is something like this. Take A equal to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. Or I would say,
A contains zeros, right?
way better, I write it this way. Let me write it this way. A is the set of all 2 power n minus 1 n greater than or equal to 1 or 0, whatever. Then what is binary A? This is nothing but this 1, 1, 1, 1, 1, 1. And if you care to add leading 0 digits, that's not a problem. It's just adding 0 star. But unary A, okay. In fact, length of unary A is not ultimately periodic, which is basically same as A. This 2 power n minus 1. This grows too rapidly with n, and therefore This cannot contain ultimate periodicity. Okay. So this is, B is false. So B is false. What about A? Or you could simply take 2 power n instead of 2 power n minus 1. So it is 1 followed by many zeros, 1 or more, 0 or more zeros, whatever, anyway, it doesn't matter.
The A is true.
It's true. Why?
Unary A is regular, so unary A will have to be ultimately periodic.
Hmm.
So we know that if n belongs to A, then n plus p belongs to A. So we just do the divisibility construction.
Hmm. So A is true. So unary A is regular, which means A is ultimately periodic. Okay. A is nothing but length of unary A. So I can write A as some numbers A1, A2, let's say AK, and then how shall I write it? Maybe I write it this way. Set of all numbers n BL for some B1 through BL modulo P and n greater than equal to some n naught. Okay. This is the definition of ultimate periodicity. Okay. So now given this, how can I construct a DFA for binary? Okay. So it's not difficult, but up to n0, I may do something like this. Okay, so n0 levels or n0 minus 1 levels, whatever. Okay, so I will draw a complete tree. 0, 1, 0, 1, 0, 1. Now some of this will correspond to the smaller numbers A1, A2, AK. So maybe this is A1, this is A2, this is AK, something like that. Okay. Then I have a mod P cycle. Okay. And I will consider B1, B2, BL. So make these things accept B1, maybe this is B2, this is BL, and so on. Okay. And inside this, what kind of transitions I will have? So it is same as divisible by 3 and that kind of stuff, right?
Yes, sir.
Okay. And from here also you will have some jumps here. 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 Okay. Upon reading 0, upon reading 1. Okay. Okay, so that's the basic construction idea. Anyway, so we can manage with finitely many states. Okay. So this is, if unary A is regular, then binary is also regular. Okay, so prove that no infinite subset of this is regular. This is fairly straightforward. In our proof of a power n, b power n, this entire set, we have taken a power k, b power k, u equal to epsilon. Okay, so if everything is allowed, we took a power k, b power k. We took this as v, this as w, and u equal to epsilon. But for
Sir, we can take a power k prime, b power k prime for some k prime greater than k.
so that's only I would say, because it is infinite. I will have some a power k prime, b power k prime for k prime greater than equal to k. K itself need not be there, but now I can proceed exactly in the same manner. V, W, here u equal to epsilon. Okay. The rest is exactly the same. Okay, so this is fairly straightforward. Now, this is a question. Prove or disprove there exists a language L. If necessary, you can assume that this language is over A comma B. Anyway, such that no infinite subset of L or its complement is regular. Of course, the first choice sounds like a power n, b power n, because in the earlier exercise we have proved that no infinite subset of that a power n, b power n is regular. But what about the complement?
Sir, it is the complement of what, sir? Sir, it is, whose complement are we talking about? The is infinite subset.
Yeah, this one side is fine, right? No infinite subset of this is regular.
Yes, sir.
What about the complement of this? Oh, I see.
Sir, complement of L itself?
Yeah. No. So definitely the complement of L is not regular, because regular language
Yes, sir.
closed under complement. But is it that the complement of that L, a previous exercise, has no regular infinite subsets? Is it true or not?
Okay, sir. Okay, sir.
If it is not, then you have to think of another example. Okay, so if L is this, this part is true. So what about complement?
Sir, sir, a power k means is a infinite subset of its complement, and it is regular. So no infinite will not hold true in that case.
So not L contains, for example, language of A plus, actually A star, also language of B plus, A plus. Okay. Agree or not? Also language of AB plus. No, not AB plus. AB plus. So this is not true. Okay, so next question is how can I find a language L for which this condition holds? Anyway, we are running.
You can disprove it, right? Because language of A plus and language of B plus, they are completely disjoint. And as we say that the language L has no infinite subset, which is regular. So L will not contain A plus, and L will not contain B plus. So they will have to be in not L itself. So not L will.
No, so what is your final conclusion? There cannot exist in such language. Is that so? Anyway, we are out of time already. Okay, so what I will say, just give you a hint. Consider this L, consider this L complement. Okay, so L contains strings of length 0, not L contains strings of length 1. Then L contains all strings of length 2 and 3. This will contain all strings of the form 4 to 7. This will contain all strings of length 8 to 15, 16 to 31, something like this. Okay, keep on doing this. Then 32 to 63 and so on, something like this. Okay. So if I consider L, take any language, any alphabet. Okay, it may be unary alphabet, it may be binary alphabet, and then let L consist of all strings of length 0 or 2 to 3 or 8 to 15 or 30 to 63 or whatever comes on 28 to 55 and so on. So now you claim that neither L nor the complement of L can contain and I would say no infinite subset of L or not L. For both this is true, can have that ultimate periodicity in terms of length. Okay, because these gaps are increasing. Gap length is 32, here the gap length is 64, next gap length is 128. Okay. So this is actually true. Okay. Okay, so let me stop here because we have already late by 5 minutes. Okay, so there are some other exercises. This was given in some mid-sem or class test paper. So I will give you a reference and this you think. Okay, so let us stop. This construction is clear, right?
Yes, sir.
Okay, fine.
Sir, but this construction is not for general L.
No. This is a there exists statement.
Okay, sir.
Okay, so I gave an example and I am done. Okay, so let us call it a day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Yes, sir.